So on a previous slide, I had a nice overview of lipid metabolism. And I sort of indicated that whether it was exogenous or dietary sources or endogenous sources of triglycerides, it kind of really didn't matter once you got into the cells. So what we're going to rectify now is understanding, well, how do we consider endogenous sort of lipid sources from the time you put something into your mouth to the time that it finally makes its way out of your GI tract. And so this first video here is going to be talking specifically about your gastrointestinal tract. And then once we get into the bloodstream, we'll have another video that talks about lipid transport in the bloodstream. So things are a little bit more complicated when you have hydrophobic molecules that you need to consider. So this is going to be a picture that we're going to kind of refer to, but I sort of want to walk you through it before we sort of talk about it with some words here. So we're focusing now on the stomach and the small intestine. So when you consume dietary fat, that also is going to contain triglycerides and triglycerides and cholesterol, right, into your stomach here, okay? You're going to have these micelles that are in your stomach. We're going to talk about how those micelles form, kind of how that's going to aid in digestion. So we'll talk about digestion in the stomach. And then once you get into your small intestine, remembering your gut tube is just a single cell layer thick. So we need to talk about how we've got these micelles that are full of lipids like triglycerides and cholesterol, how we're going to get them across and into the intestinal epithelial cells, and then ultimately offload them for transport in the bloodstream. So at that point, we'll stop this video and there'll be a second video that talks about lipid transport within the bloodstream. So that's going to sort of be what we're talking about here is sort of the dietary GI tract component for lipid metabolism, so those exogenous sources. So the first thing that we're going to talk about here is the stomach. Largely just conversational here, talking about some important pieces. And some of the keys here are that dietary lipids are quite hydrophobic. Okay? And the problem is your digestive environment, as is much of your body, is fairly hydrophilic. So your digestive environment is fairly hydrophilic. Okay, and specifically if we're talking about your stomach, there's a low pH. So how do we basically have a connection between these hydrophobic molecules that need to be metabolized, digested, interacted with in a hydrophilic sort of space? So the question is how do we connect or have these interact? Okay, and I'm going to have a 3-part story here. So I'll tell you what those 3 parts are, and then we'll go to each one in a little bit of detail. The first thing is we can have physical mixing, and that's going to aid in the connection and interaction of these two hydrophobic and hydrophilic sort of situations, so physical mixing. Then we can think about emulsification. And lastly, we can think about the need for enzyme chemistry. So this is going to be phospholipase enzymes. Okay, so talking first about this concept of physical mixing, right? We are going to use peristalsis for this. That's the rhythmic contraction of your GI tract that allows us to physically mix things together. And the purpose of that physical mixing is we are going to increase that surface area of the lipids with water, which is going to be important because we have enzymes in that hydrophilic sort of space. So we need to have those surfaces interact. You can imagine this. I'm going to use a salad dressing analogy for a bit here. If you made salad dressing the old-fashioned way and you sort of had oil and then water and vinegar that you mixed, if you let that sit for a while, that oil and water layer is going to separate. And if we have chemistry happening, chemistry is only going to happen at the interface of the hydrophobic and hydrophilic sort of layers that we have there. I guess in salad dressing, it would be the opposite. The hydrophobic would be on top, right? And so if we've let this separate, there's not a lot of surface area that's interacting. However, if you were to shake that salad dressing, you would greatly increase the amount of surface area in that lipid that's contacting the water. And the same is happening when your stomach does its contractions and we have that peristalsis. Okay. The other way that we can help is emulsification. And the idea is that we are going to add in nature's soap. Okay. So nature's soap is right here. These are bile acids. I'm going to zoom in here so we can kind of look at the structure. Hopefully you look at this and you're like, that kind of looks familiar. I've got 4 fused rings here. We see those in steroid molecules. Specifically, this is derived from cholesterol. And we're basically going to have some cholesterol derivatives that we attach kind of some other R groups that are on here to create these bile acids. So bile acids, importantly, are derived from cholesterol. So cholesterol gets a really bad rap, but cholesterol has tons of important purposes, one of which is to make these bile acids. And another thing to highlight is bile acids are the only way, so the only mechanism to dispose of excess cholesterol. Okay, so I'm going to come back up here. I'm going to have to zoom in quite a lot on this picture, but to sort of show here, just a little bit about bile acids. So here's our bile acids. Bile acids are synthesized in the liver. They are stored in your gallbladder. And when needed, from a digestive standpoint, they are secreted into your GI tract. So gallbladder is not absolutely necessary. There's people who have their gallbladders removed, but you can think of this as then not having a spigot where you can control the influx of bile acids into your GI tract. It's basically just a drippy faucet that's always on. Okay, but that's sort of how we can help with this emulsification process. Okay, so highlighting some of the pieces that I've sort of said there. This is again what bile is. Bile is very rich in those bile acids. Okay, so this is synthesized in the liver and then stored in our gallbladder. Okay, so going back to our salad dressing analogy, right? If you make salad dressing sort of the old-fashioned way with like a packet of seasoning, and then you mix water and vinegar, which are hydrophilic, with oil, which is hydrophobic, right? The only way to sort of get it to mix is to physically shake it. Well, oftentimes you can buy salad dressing in the grocery store that doesn't require you to shake it. It just kind of looks like it's always mixed. And that's because they've added emulsifying agents to that to sort of get that to mix. The same is sort of true when you think about if you were to get milk right from the cow. If you let that sit, it will separate and the cream and the fat will go to the top. When you get milk that's kind of been pasteurized and homogenized, okay, that allows those fats to be sort of mixed and dispersed throughout. So the last little piece here to highlight, when we're thinking about digestion, there's phospholipase enzymes that start doing their chemistry in the stomach, okay, and their purpose are to hydrolyze those ester linkages in triglycerides. So we've got our glycerol backbone, we've got our fatty acids that we have here. We're going to hydrolyze those ester linkages, and we're going to make those prepared to be in their monomeric or form that can be uptaken in the small intestine. So we're going to hydrolyze these ester linkages in our triglycerides, and that's important because this is necessary for their uptake from the small intestine. Okay. All right, so let's move on then to the small intestine, and we're going to talk about sort of what happens in that region. So key piece here to sort of think about the small intestine, right? A theme that we've seen before is that only monomers can exit the GI tract. So only monomers can exit our GI tract. Okay? And again, unless you have leaky gut. Leaky gut means bigger things can get out, and that again is problematic. Okay? So let's think about our different exogenous dietary molecules we might be taking in. We might be taking in carbohydrates. Those need to be broken down into monosaccharides. Okay, we might have lipids. And we're considering, again, about 90% of lipids to be triglycerides. Okay, these need to be broken down into fatty acids or diacylglycerols or monoacylglycerols. Okay, so we can't have not everything sort of become off, but we cannot have a triglyceride exit your GI tract. Okay, and then the last thing is we are going to have proteins. Okay, proteins must be broken down into their component amino acids. So I'm going to compartmentalize these. These, again, are 3 molecules we know we can use for fuels. Okay, but carbohydrates and lipids are meant to be fuel molecules. So these are meant to be fuel molecules. Okay, proteins, on the other hand, are not meant to be fuel. Okay, they are meant to be building blocks. Let's see, I'll put this down here. These are meant to be building blocks. Now, it's not to say that we cannot metabolize them for fuel, but that is not their intent. Okay, so what I'm going to do with the rest of this slide here and talking about how we get things out of your GI tract is we will have a focus on some new biochemistry that we're talking about with sort of lipid digestion and sort of getting that into your bloodstream. But I want to review some aspects from carbohydrate and protein metabolism and highlight some important stories. So kind of a theme that we'll also have in what we're talking about here is food additives. And so we're going to talk about specifically some carbohydrate food additives, sort of some protein-based food additives, and then some lipid-based food additives. So I'm going to start sort of with the story that is carbohydrates over here. So we're going to just review and talk about some interesting kind of stories of stuff we've talked about with carbohydrates. And then we're going to talk just very briefly about some stuff with proteins. And then I'll save the new stuff, which is lipid, for the very end, and we're going to talk about some new pieces that we haven't talked about. Okay, so when we think about monosaccharides, right, we want to think about only, again, monomers coming out of our GI tract. So when we're talking about something like fiber, fiber is going to be something that has beta 1,4 glycosidic linkages, and that's going to mean that we're not able to hydrolyze that glycosidic bond, and that's why it's fiber. It doesn't get broken down into its monomeric form by you in your GI tract, okay? But here's some aspects of fiber, why it's important. It allows us to move our intestinal waste. That would be hugely problematic, right? We're going to talk about poop in biochemistry, right? If you are not pooping at least every other day, that's an indication that you are not moving your waste products out of your GI tract quickly enough, and that can be problematic. You don't want those waste products sitting against your delicate, GI tissue for long periods of time. Ideally, you should poop once a day, but if you're not pooping once a day, should be every other day. You can even poop more than once a day, and that's okay as long as it's well formed and so forth. But again, having your bowels not move fast enough can have other problems as well. Now, another reason that fiber is important is it is food for your microbiome, so your microbiota. I'm going to zoom in here to kind of finish this story so I don't run out of room here. Okay, so when we think about some terms that we've talked about, when we talk about food for your microbiota, again, fiber that you can consume can be food for your microbiota, but anytime you hear the term prebiotic, that's referring to something that you can consume that is a food for your bugs in your belly. Your microbiota, when we're talking about those are probiotics. Okay? Importantly, probiotics should live in your large intestine, not in your small intestine. Probiotics, bacteria that find their way into your small intestine, that's problematic. We call that SIBO, or small intestinal bacterial overgrowth or outgrowth, where they're growing in a spot that they're not supposed to. This can cause a lot of bloating and so forth. Those bacteria are not meant to live outside of colonizing your large intestine. Okay, a couple of other kind of pieces to highlight: that anytime you get something that is indigestible by you, okay, so something is indigestible by you, the bugs in your belly, in your large intestine, are going to have a go at it. Okay, sometimes this can cause gas and bloating. As an example, we talked about lactose intolerance, right? Lactose being the disaccharide of glucose and galactose, linked by a beta-1,4 glycosidic linkage. Now, if you have the enzyme lactase, you can break that linkage. You get free glucose and free galactose. Those can exit your GI tract. If you don't have the enzyme lactase, then lactose makes its way down into your large intestine, and the bugs there try to have a go at it. Now, they're not as gentle when they try to break it down, and they generate a lot of gas, a lot of acids, and that can be problematic and lead to a lot of the symptoms that you see for somebody who is lactose intolerant. Okay. One of the last little pieces to talk about here is thinking about one of the food additives that we've talked about, which is sucralose. So sucralose is a chlorinated version of sucrose. Remember, sucrose being the disaccharide of glucose and fructose. And so we take 3 of those OH groups that are on that disaccharide and replace the OH groups with chlorine. What that does is it makes this molecule not able to be metabolized. So it makes its way through your GI tract. That glycosidic bond is not hydrolyzed. And so that's why it's non-caloric, because you cannot either break that glycosidic bond, or even if you got those monomers in your GI tract, there are not substrates for glycolysis or other metabolic pathways. So when we talk about food additives that are non-caloric, they're usually because they're non-metabolizable, okay? Or you use such small amounts that we consider their calorie content negligible. Well, for sucralose, it's kind of a combination of both, non-metabolizable, but it's also 600 times as sweet as sugar. So a situation where you need very, very little of it. So here's how all of this ties together and why this is potentially problematic, is there's questions as to whether sucralose is toxic to the probiotics that are living in your large intestine. Questionable evidence out there. It's not ruled out that it could be problematic for your bacteria that are living in your small intestine, your large intestine. So think about that in terms of looking at the food additives that are there, and consider that even though sucralose is not metabolizable by you, it may not be something that makes the bugs in your belly all that happy. Okay, moving over, let's review another story that we've talked about with proteins. And so another food additive that we've sort of talked about is aspartame. Okay, aspartame, trade named NutraSweet, is a dipeptide of phenylalanine, aspartic acid, and then since the aspartic acid is on the C-terminus, okay, it has that carboxylate group that can be methylated, so it makes it into a methyl ester. And here's 2 reasons why this is potentially problematic. Now, this is something that is metabolized by you, okay? There's nothing sort of abnormal about this, okay? You can break down this little dipeptide into 2 component amino acids, but because it's 200 to 300 times as sweet as sugar, you don't need that much of it. So even though it's a protein worth 4 calories per gram, it's not something that you use so much of that it really contributes to the calorie content. But here's why it can potentially be problematic. Some people have the inability to metabolize the amino acid phenylalanine. We are going to learn in our protein metabolism chapter about the metabolic disorder called PKU. Which causes, these are phenylketonuria. So phenylketonuria basically has high levels of phenylalanine that are not able to be metabolized. Okay, so they're going to sort of build up in your body, and that can be toxic. So we're going to talk about PKU, and one of the things that you need to see, anything that contains NutraSweet has to have a warning label on it telling people with PKU this contains phenylalanine, so you might need to limit its consumption. Last piece here is if you have something that's a methyl ester and you hydrolyze that methyl ester, there's the potential to produce methanol. Now, the amounts of methanol you might produce from NutraSweet are probably not significant, but still could be something that could be problematic. So we want to think about how that sort of comes into play. All right, last piece, and I know this video was getting a little bit long talking about our GI tract, is talking about what happens with these fatty acids. Okay, so problem with fatty acids is they are water insoluble. Okay, water insoluble. This is going to be a theme that we see is any lipid. If it gets into particularly your bloodstream, it needs to be complexed with a protein. So complex with a protein. And this starts here with our first foray of these fatty acid molecules into our intestinal epithelial cells. So I'm going to zoom back into this picture here to sort of highlight what's happening. Okay, so if we've got our micelles from our emulsification, our peristalsis, and then we've had some esterase activity that has made these into free fatty acids, they're going to be able to go and cross this cell membrane and get into the inside of intestinal epithelial cells. But what we're going to do is we are going to complex any of these little black sticks that we see. They represent free fatty acids. And so inside of these intestinal epithelial cells, what we're going to see is the complexing of these fatty acids. So here's a fatty acid here. Okay, so this represents a fatty acid. So this guy is a fatty acid, which is represented by these black sticks that we see sort of in our picture here. So those fatty acids are complexed with a protein that we call a fatty acid binding protein. Okay? So fatty acid binding protein is going to live in here. So it lives inside those intestinal epithelial cells. Here's how fatty acid binding proteins help. They help in two ways. First of all, they're going to increase the solubility of our fatty acids, and that's going to be a theme that we're going to see. And the second thing that they're going to do is they are going to sort of make it seem like there is no concentration of fatty acids in the cell, so they're going to help with facilitated diffusion. So they're going to help with facilitated diffusion. Okay? And so that's going to help pull in those fatty acids from the GI tract and kind of get them packed into our intestinal epithelial cells. We'll get to this kind of on our bloodstream slide, but noting what happens here is what we're going to do then is reassemble them into triglycerides once we've got them inside these intestinal epithelial cells, and then we're going to package them into lipid transport vehicles that we call chylomicrons. All right, last little thing is talking about one more food additive, okay, that we're going to have as a fat substitute. Well, you might say, why do we want to have a fat substitute? Well, because real fat does two important things, okay? It contributes texture and it contributes flavor. And I have flavor in quotes here because fat really by itself doesn't have any flavor. If you were to take some cholesterol or lard or anything like that, it really has zero flavor by itself. But many molecules that are flavorful are hydrophobic themselves, so they like to associate with fat. Okay, so if you have heard of olestra, also called olein, this is a fat substitute. So if we think about fatty acids, right? We've got a glycerol backbone that has 3 OH groups that we hook fatty acids onto because we make an ester linkage, okay? What we're going to do to make this fat substitute is we are going to take a sugar. We're going to take a sugar that has a lot of OH groups on it. And we are going to attach fatty acids to those OH groups. So let's replace one of these OH groups now with an O, and then we are going to attach a fatty acid onto it. So imagine doing this all the way around this wheel, if you will. Okay, we have a molecule that sort of is fat-like, but here's sort of the big key here. We cannot break this linkage. Theme: if we've got molecules that we cannot break apart into their monomeric form, they are not going to be changed as they go through your GI tract. Yes, the bugs in your belly and your large intestine might try to have a stab at it, but they're largely going to have problems with it. If you look at the warning label for anything that contains olestra or olein, one of the things it will tell you is warning may cause oily, runny stool. And the reason is you've essentially put that fat molecule into your GI tract and it cannot be broken down, so it cannot come out of your GI tract. Why it's a fat-free and calorie sort of free molecule, but it's going to exit your GI tract in the same form that it came in. Oil, and again, that can cause runny stool. So the problem is when you put this in something like potato chips and make a bag of fat-free potato chips, rather than having one serving of fat-free potato chips and being like, oh, that's okay, you think, hey, those are fat-free, I'm going to eat the entire bag, and then you have some GI complications. All right, so a long sort of video here, sort of walking through the GI issues that we have to think about when we talk about exogenous or dietary fats.